Wait, is there going to be a homework check on Thursday?
Yeah.
Yeah. Yeah. Okay. Wait, Thursday's the last homework check.
Yeah, that's true.
Yeah, you are taking that. I guess not for you. You have so many more lessons and homework checks, right, Mr. Beaver?
Yes. All right, so we're going to revisit the matrix exponential. Oh, I got to turn the thing on. You got to be able to see what I'm writing.
What does the video look like?
Yeah, it's recording the screen. But did I tell you, I've had people come in here when I recording the video, and when they walk past here, they go.
That's what I would have done. That's what I would do, Mr. Beaver.
So they're not on the video.
I always thought it was recording there. I thought it was like a...
Have you ever watched one of the videos?
Yeah, but I always just assume it's that screen, not the little one.
It's the same screen.
Because that's what I see. That's the screen.
It's not even a screen.
Wait, 8.4 part 2?
Yeah, so we're going back to, in chapter 8, when we talked about systems, we talked about the matrix exponential and how we can use a matrix exponential to solve systems of differential equations using the matrix exponential. So a reminder, some of the properties of the matrix exponential. E to the AT. A is an n by n matrix. Is, we define e to the AT with a power series plus AT plus a squared t squared over 2 factorial plus a to the third t to the third over 3 factorial plus, and we go up to a sub k t to the k over k factorial. And we could say this is the summation k equals 0 to infinity of a to the k t to the k over k factorial. Just, it's a power series for e to the x, but, or e to the some number times x, but instead of a number we have a matrix. So we're computing powers of that matrix. If, the reason we talked about it in chapter 8 is that if x prime equals ax, a system of differential equations, e to the AT is a solution to the system. So that's why the matrix exponential is important and useful. The derivative of e to the AT is a e to the AT. Behaves just like we expect. And we can figure that out by doing term by term differentiation of our definition. And finally, e to the AT is a fundamental matrix of x prime equals ax. And remember from chapter 8, the fundamental matrix of our system was an important matrix. We used the fundamental matrix when we talked about variation of parameters with systems. The fundamental matrix is the one we have to do. We had to invert it and multiply it and integrate and then multiply again. So there was a lot of stuff involved there. Well, we saw that the computation of e to the AT from the definition requires computation of power series and then making a connection between the power series we see and some closed form representation of the power series. So we had a power series and we needed to recognize, oh, that's the power series for sine, or that's the power series for cosine. And sometimes when we do these computations, the e to the at, the matrix A, the elements of the matrix are sums of power series of various functions. So it gets kind of tricky computing the matrix exponential from the definition. So we're going to look at an alternate way to calculate the matrix exponential. If we can calculate the matrix exponential in a different way, then we can solve a system of differential equations in this different way. So we know that x equals e to the at is a solution to x prime equals ax. And e to the a times 0 is the identity matrix. And we can see that from the definition of e to the at. If we put in t equals 0, we just get the identity matrix. We go back here, put in t equals 0, we just get the identity matrix. So this tells us that x e to the at, x equals e to the at, is a solution to the initial value problem, x prime equals ax, with x of 0 is the identity matrix. Now we're going to suppose that x of s is the Laplace transform of x of t, which is the Laplace transform of e to the at. So we're going to apply the Laplace transform to our initial value problem. And we know how to apply a Laplace transform to initial value problem. We get to our IVP, and we get x of s minus x of 0 equals a x of s. So we're just applying our Laplace transform to this. And I'm going to substitute these values. So we get s x of s minus a x of s, and x of 0 is I, so we get an I there. And I'm going to rewrite this s x of s minus a x of s as a matrix equation. So I'm going to say this is s times the identity matrix minus a times x of s, and that equals the identity matrix. Now to solve a matrix equation, what we do is we multiply both sides of the equation by the inverse of this thing. So we're going to multiply by si minus a inverse. So it's kind of like dividing with matrix equations, kind of like dividing by that quantity that's multiplying our x of s. We don't have division for matrices, so we multiply by the inverse. So we get si minus a inverse times si minus a times x of s equals si minus a inverse times the identity matrix. Well, the inverse matrix times the matrix itself just gives us the identity matrix, And the identity matrix times anything is just that thing. So we get x of s equals, and the identity matrix times this si minus a inverse gives us si minus a inverse. Well, this tells us if this is the Laplace transform of x, that tells us the Laplace transform of x of t equals, which is the Laplace transform of e to the at, equals si minus a inverse. So to find x of t, or to find e to the at, we're going to do the inverse transform of this. So e to the at, this thing we're trying to calculate, is the inverse transform of si minus a, inverse. So doing this matrix thing, si minus a, that's pretty easy to do. We did that a lot when we were solving systems of equations. We were finding the eigenvalues and eigenvectors. Finding the inverse of a 2 by 2 matrix is easy. Computers are very good at finding the inverses of other matrices. So this gives us a nice way to calculate. We take the inverse transform of this, whatever we get for this si minus a inverse. We take the Laplace transform of each element, or the inverse Laplace transform of each element, and we have our matrix exponential. So generally, this is nice because generally matrix operations are easier to compute than power series manipulations. So this is a nice alternative way to find e to the at. Kind of an interesting application of Laplace transform. Yes?
So this one we kind of, when we said that x of 0 equals I was an initial condition.
Right.
So we do still have to have these conditions for this?
Yes. We need an initial value problem. Just like to solve differential equations with Laplace transforms, we use Laplace transforms for initial value problems. So I just want to go through an example of doing this, this computation, find e to the at. And I just want to emphasize, by finding e to the at, we are finding the solution to this system of differential equations. We want to find e to the at for this a. So I'm going to calculate or compute si minus a. That is s minus 4. Should it be 2? Negative 1, s minus 1. Is that right? Yeah, we're subtracting, right? So si minus a inverse, I need to find the determinant of si minus a. Well, that's s minus 4 times s minus 1 minus, so it's going to be plus 2, minus 2 times negative 1. Which gives me s squared minus 5s plus 6, which I'm going to factor to s minus 2 times s minus 3. So si minus a inverse is 1 over the determinant, 1 over s minus 2, s minus 3, times the matrix we get when we switch these two, change the signs on these two. So we get s minus 1, negative 2, 1, s minus 4, which is s minus 1 over s minus 2, s minus 3, negative 2, s minus 2, s minus 3, 1 over s minus 2, s minus 3, and finally s minus 4, s minus 2, s minus 3. There's our matrix that we're going to take the inverse transform of. But before we take the inverse transform, what do we need to do here? Partial fractions 4 times.
Seems like something computers are very good at.
I hope that some of our students are really good at that by now too. Some of them. So when we do partial fractions here, we get 2 over s minus 3 minus 1 over s minus 2. 2 over s minus 3 minus 2 over s minus 2. 1 over s minus 2 minus 1 over s minus 3, and negative 1 over s minus 3 plus 2 over s minus 2. So now we take the inverse transform of that quantity, and we just take the inverse transform to, term by term, and we get 2e to the 3t minus e to the 2t, 2e to the 2t, did we do that right? No, 2e to the 3t minus 2e to the 2t, e to the 2t minus e to the 3t, and minus e to the 3t plus 2e to the 2t. Yes.
That's the inverse transform.
Inverse, yes. Sorry. So if we were to have calculated e to the at using our power series, we would have gotten sums in there that somehow we would need to separate, or we'd need to separate in order to see what the closed form solution to each word is. But that's not a terrible way to do this calculation. This is a pretty complicated matrix exponential, but with just some straightforward algebraic techniques. You might not like the straightforward algebraic techniques, but they are generally straightforward algebraic techniques that we can apply. So arguably a nicer procedure than using power series. I think inverting a 2 by 2 matrix and doing some partial fractions a little easier than multiplying a squared, a to the third, a to the fourth, etc. Yes. Could we use our
Like, could we have it just a partial fraction staying the same?
Well, yeah, but you still gotta do it for them.
Yeah, I'm trying to figure out how I want to do that, because if if we have access to our computers, then we have access to our computers for everything.
Okay.
Maybe I could have a computer open up here, and you could come and sit and do your calculations and.
That'd be so Steven, tell Stancy, go.
Yeah, Steven, just leave yours in, like, press enter so I can read it. That way, when I get mine wrong, I can be like, oh,
you could
that's
put
how
some
we do
partial
it.
fraction like calculations up there.
Yeah, just put like 10 random ones.
Just some
up
random
there.
ones that you
Yeah.
can, like a partial fractions bank
Yeah.
instead of a word bank.
Yes, that would be
So
amazing.
you have to do one.
Please give us a partial fraction thing.
I need to figure out something, and I don't know if you've worked on the homework from Friday,
Yeah.
but solving those systems of equations. If you use Kramer's rule, it turns out pretty nice. But if you don't use Kramer's rule, it's not very nice.
Is that just your Kramer's rule?
I don't solve problems anymore. I don't power series anymore. We want that ending made it easier.
No, Kramer's rule is like a godsend. I don't have to
That's
do
it?
anything.
I'm like, we're done forever?
It's so satisfying to done.
And look at your homework assignment.
Wait, like, it was
Wait, is it 9 to 12?
It was like
No. 9, 10, 11, 12. 4 problems.
That's
Okay.
really